Hello friends. So today we are going to discuss questions from heat and thermodynamics, and all these questions are from the year 2019. Total questions are 21, and all these 21 questions are from the mains. So the first question, it states that a 15 gram of nitrogen gas is enclosed in a vessel at a temperature of 27 degrees centigrade. Amount of heat transferred to the gas so that RMS velocity of the molecules is doubled is about. Take R as 8.3. So this question is directly based on the formula, because we have to find out or make a relationship or write a relationship between the RMS velocity and with respect to the temperature. So we start from the formula. We know that our RMS velocity which is given as VRMS is equal to square root of 3RT divided by M, where M is the molar mass, R is the gas constant, and T is the absolute temperature. And it says that we need to find out the heat transferred so that the RMS becomes root means square value become root means RMS velocity rather becomes double. Okay. So it means, let us suppose our new RMS velocity is V prime RMS, and this V prime RMS will be equal to twice of our VRMS. That is a given condition. And this new RMS velocity is supposed at a temperature of T prime, and VRMS velocity is at the temperature of T. So we can easily find out the ratio. So we can say our V prime RMS divided by VRMS will be equal to our temperature prime oblique temperature, and the ratio is given as 2, so this will be equal to 2. Therefore from here we can say that our T prime is equal to 4 times T. So we got the relationship of the temperature T prime as well as the original temperature T. Okay. And we are given the initial temperature is given to us. Initial temperature, that is of T, it is given to us as 23 degrees centigrade, or we can say 300 Kelvin. Therefore we can say our final temperature which is our T prime will be 4 times 300, and which gives us 1200 Kelvin. And we are going to find out the heat transferred So we can write that our heat required is, because we have a enclosed vessel, so there will be a constant volume, therefore we can say heat required, that is our Q, will be equal to N C of V multiplied by delta T. Okay, where N is our number of moles which we can calculate. We can say N is equal to number of moles. So this comes as our given mass divided by the molar mass. Given mass is our 15 and molar mass is our 28. So number of moles will be approximately equal to 0.536. And the gas given to us is a nitrogen. So we know that our nitrogen is our diatomic. It is a diatomic gas. Therefore, as the vessel is closed, so we can write our C of V will be equal to 5.2 multiplied by R. And delta T is our difference in temperature. So we can say our delta T is equal to our final temperature T prime minus initial temperature T. Final temperature is our 1200 minus 300. So this gives us 900 Kelvin. So now we can easily find out our Q. So number of moles were our 0.536 multiplied by 5/2 times R. R is said to be our 8.3 and delta T is our 900. So this Q will be approximately equal to 10 kilojoules. So option A is correct. Next question. It states that a mixture of 2 moles of helium gas, atomic mass 4U, and 1 mole of argon gas, atomic mass 40U, is kept at 300 Kelvin in a container. The ratio of their RMS speed, that is VRMS helium to VRMS argon, is close to. So this once again is based on our formula, that is our RMS speed. So you can say the RMS speed given as VRMS will be equal to 3RT divided by M and its square root. Okay, and here temperature is same, so we can say from here that our VRMS is proportional to square root of M. Okay. And we can divide this formula as per our helium and argon gas, though we can write it directly from in the ratio. We can say our VRMS helium and VRMS argon will be equal to our square root M of argon and we have M of our helium. and the molar masses of argon and helium are given to us. So we simply substitute them. We get this as 40 upon 4, which comes as square root of 10, approximately 3.16. So option C is correct. Next question. It states that a Carnot engine has an efficiency of 1/6 when the temperature of the sink is reduced to by 62 degrees centigrade. Its efficiency is doubled. The temperature of the source and the sink are respectively. So here we are given a Carnot engine and we are talking about its efficiency. So we can write that our Carnot efficiency nu is equal to one minus T2 upon T1, and here T1 is the temperature of the source. T1 is our source temperature, and T2 is our sink temperature, and these both temperatures are in Kelvin. And initially we are given that efficiency is 1/6. Therefore we can simply substitute it 1/6. So it get 1/6 is equal to 1 minus T2 upon T1. So from here we get the ratio of T2 upon T1 is equal to 5 upon 6. Now it states that the temperature of the sink is reduced by 62 degree. Its efficiency is doubled. Okay. So under second condition, the temperature of the sink is reduced by 62 degree. Okay. So we can say, and let us temperature of our sink. So we can say sink temperature in the second case is, let us suppose, T2 prime, and this T2 prime will be equal to original sink temperature minus 62. Okay. And it says that the efficiency is doubled. Okay. So you can say efficiency is equal to, suppose, nu prime will be equal to 2 times original efficiency, which comes 2 into 1/6, giving us 1/3. But the formula for the efficiency is going to remain same. So we can say our nu prime will be equal to 1 minus T2 prime divided by T1, and this comes as a 1/3. So from here we can say that our T2 prime upon T1 is equal to 2/3. In place of T2 prime we can write T2 minus 62. So from here we get T2 minus 62 upon T1 is equal to 2/3. And we know from here we can write that our T2, sorry, not T2, but yeah, T2 is equal to 5/6 times T1. So we substitute here T2, we get this as our 5/6 times T1 minus 62 upon T1 is equal to 2 by 3. Now it is a simple calculation. We can write this as 5 by 6 times T1 minus 62 is equal to 2 by 3 times T1. And this gives us 5 by 6 upon T1 minus 2 upon 3 times T1 is equal to 62. And our 6 will be LCM, so this will be coming as 5 minus 4, that is equal to our 1 by 6. So we get our 1 by 6 times T1 is equal to 62. This gives us that our T1 will be equal to 372 Kelvin. Now we can easily find out our T2. So T2 was our 5/6 upon T1, giving us 5/6 multiplied by 372, which gives us 310 Kelvin. Okay, so temperature in degree centigrade, so we can just, you can say minus, so we get our T1 will be equal to our 99 degree centigrade, and our T2 will be equal to, this is 310 and 273, this will be close to 73, 7 and 37 something, yeah, 37. So we are going to have source and sink. Okay. So we get T2 will be our 37 degree centigrade. So we get our option number B is correct. One second. Sink is our T2. Yeah, so option B is correct. Correct. Next question. It states that a sample of ideal gas is taken through a cyclic process ABCA as shown in the figure. The change in the internal energy of the gas along the path CA is minus 180 joule. The gas absorbs 250 joule of heat along the path AB and 60 joule along the path BC. The work done by the gas along the path ABC is. So we are given a PV diagram, and this PV diagram, it is a cyclic process. So it starts from A, goes to B, C and come back to A. And we are given that internally change along our path CA. This path internally change is minus 180, and heat absorbs from AB is given, and for path BC is also given to us. Okay, we have to find out the work done through the path ABC. Okay, so we have to find out the work done along this path ABC. So basically this is a cyclic process. So total change in internal energy is equal to 0. So we can say cyclic process, and therefore change in energy along the cyclic process will be equal to 0. And we are going to for our first law of thermodynamics. So from first law we can write that our delta Q is equal to delta U plus W. And here we know our delta Q is the heat added, delta U is the change in internal energy, and W is the work done by the gas. And for the path CA, we are given that the change in internal energy, so we can say that for path CA, we are given that our delta U CA is minus 180 joules. And we know that it is a cyclic process, so we can write the individual, you can say, change energy for each path, that is AB, BC and CA, that will be equal to 0. So we know that our cyclic process, we are going to have delta U AB plus delta U BC plus delta U CA is equal to 0. And delta U CA is our minus 180. Therefore, we can write that our delta U AB plus delta U BC is equal to 180 joules. And the heat absorbed for their respective path is also given to us. So we are given that our path AB, we are given that our QAB is equal to 250, and path BC, we are given QBC, which is equal to 60 joules. So respectively, for each path we can find out, or we can say we can use our first law. And for similarly for path AB, we can write this as QAB will be equal to delta UAB plus work done for the AB, and QAB is 250. So we can write this as 250 is equal to delta UAB plus WAB. And for path BC, we can write our QBC is equal to delta UBC plus work done for our BC. And QBC is 60, so this comes as 60 is equal to delta UBC plus WBC. And for the along total path ABC, we can write that total work done along ABC, let us call this WABC, will be equal to WAB plus WBC. And so we can just WAB will be equal to let us call this equation number 1 and this is equation number 2. So let us add equation 1 and 2. So we can say 1 plus 2 will be giving us 310 is equal to delta UAB plus delta UBC plus work done for AB plus work done for BC, and this summation is our 180 degree, and this is our total work done. Here the summation is 180, therefore we can substitute it. we get this as 310 is equal to 180 plus our WABC, which gives us WABC is equal to 310 minus 180, and that will be giving us 130 joules. So option B is correct. Next question. It states that when heat Q is supplied to a diatomic gas of rigid molecules at constant volume, its temperature increases by delta T. The heat required to produce the same change in temperature at a constant pressure is. So in this case, we are given that first is at constant volume and then it is at constant pressure. Okay. So from we can write that at constant volume our C of V is equal to 5 by 2 times R. From here we can find out our C of P, that is constant pressure. Constant pressure is our C of P, which will be equal to C of P plus R, and this will be giving us 7 by 2 times R. And we also know that the heat at constant volume, we know that heat at constant volume is suppose given as Q will be equal to N C of V multiplied by delta T, and it states that there should be same change in temperature at constant pressure. Therefore we can say that heat at constant pressure at for same change in temperature, that is our delta T, and let us call this as our Q prime. So we can say our Q prime will be equal to N C of P multiplied by delta T, and let's take their ratio. So we get our ratio, that is our Q prime oblique Q is equal to N C of P multiplied by delta T, and here we have N C of V multiplied by delta T, and this N delta T cancels out, so this comes as our C of P and C of V, and we already know C of P is our 7 by 2 times R, and C of V is our 5 by 2 times R, and here this R, 2 and 2 cancel out, and this comes as our 7 by 2. Okay. That was our ask for. So, 7 by 5. Therefore, we can write that our Q prime will be equal to 7.5 times Q. Therefore, option D is correct. D is correct. Next question. It states that n moles of ideal gas with constant volume heat capacity C of V undergoes an isobaric expansion by certain volume. The ratio of the work done in the process to the heat supplied is. Okay. So basically it is isobaric. So we know that the work done will be equal to our P times delta V, and heat supplied will be equal to Q times our, because it is isobaric, so Q is equal to N C of P delta of T. So let us start from there. So we can say we are having a isobaric process, and which basically means pressure is constant. Therefore, we can say our work done, which is our W, will be equal to P times delta V, and our heat supplied which is our Q will be equal to N C of P multiplied by delta T. And we can use our ideal gas law, and from there we can say that our ideal gas law, this gives you PV delta V is equal to NR times delta T, and we know that our work done is equal to P into delta V. Therefore, we can write that our work done, which is P delta V, can be written as NR times delta T. We have to find out the ratio. Therefore, we can write that our W upon Q is equal to W is our NR delta T, and Q is N C of P times delta T, and this delta T, one second, okay, it is in terms of Cp. So this is our delta T, so we can write this as our NR delta T, and this will be N our Cp, sorry, not Cp but Cv, N times, one second, N times Cv plus N times R, and this comes as our delta T, which can be written as our nRT C of V times N times R. So this is the ratio of our work done divided by the heat. So option D is correct. Next question. it states that following figure shows two processes A and B for a gas. If delta QA and delta QB are the amount of heat absorbed by the system in two cases, and delta UA and delta UB are the change in internal energy respectively, then we have to find out what will be their respective relationship. And PV diagram is given to us. So in this we can easily see that our initial state and final state for both the processes A and B is same. Therefore, their internal energy will be same. So we can say that our initial and final states for both A and B are same. So we can write that our delta of UA is equal to delta of UB. So this is a relationship between their internal energy. Now we come to this heat. So from the graph itself we can see that work done for A will be greater than work done for our B. Okay, based on their, you can say area also, we can just say it. And we can say that work done during A is greater than work done during B. And from first law of thermodynamics we can write that from first law, so I can write that work done for our A is greater than for work done from B. And from first law we have our delta Q is equal to delta U plus W. So we can write this first law in two terms. For process A, delta UA plus work done for A, and for our process B, delta UB plus work done for the B. And comparatively this UA and UB is same. Secondly, our WA is greater than WB. Thus we can write that our heat for our A will be greater than for the heat of our B. So we have internal is same, and okay, so option C is correct. Option C is correct. Next question. We are given that the given diagram shows four processes: isochoric, isobaric, isothermal and adiabatic. The correct assignment of the processes in the same order will be. Basic PV diagram is given to us. So we have processes A, B, C and D. We have to find out which belongs to which. At least two processes we can easily identify, that is process A, where pressure is constant, and our process D, where volume is constant. Okay. So it means process A will be our isobaric and process D will be our isochoric. So we can say our process A is our isobaric and we have our process D and that process D is a constant volume, so we have this is isochoric. And now we are only left with isothermal and adiabatic. And comparatively, we have to remember that the slope for adiabatic is always on the higher side as compared to our isothermal. Okay. So adiabatic slope will be more than isothermal. So you can say our adiabatic slope is more than our isothermal. Therefore, from the figure we can see that our B is our isothermal and C is our adiabatic. You can say our process B is our isothermal and process C is our adiabatic. Therefore, A is our, so we are going to have our in the same order it is asked. So adiabatic is our C, so this is our last one, so option B will be our correct. Okay, so we are going to have A, D, B, C. A, D, and isobaric, yeah, isochoric and isobaric. One second. Oh, no. Let me write it here. So we have isochoric, isochoric is our D, isobaric is our A, isothermal is our B, and adiabatic is our C. So process will be our DABC. Doesn't match. Very strange. Isochoric is D, isobaric is A. I think there is some isothermal is B. Sorry, DABC. My mistake. So option A is correct. Option A is correct. It was in front of me. DABC. Next question. It states that for a cyclic process CAB, as shown for a gas, the work done is equal to. So we have a graphical for our PV, and the process is cyclic, that is our CAB. Okay. And we know that the work done is also in the form of our area under the curve. Okay. Therefore, we can write that for PV diagram, work done by gas is area under the curve. Is area under the curve. And so this is a right angle triangle. Therefore, we can say that our work done W will be equal to half into base into height, which case our half, and we are going to have our, this is our 1 and this is 5, so it comes as 4 multiplied by this is 1 and this is 6, so this will be coming as 5, giving us this 4 goes by 2, this is equal to 10 joules. Option B is correct. Option B is correct. Next question. It states that half mole of ideal monatomic gas is heated at constant pressure of 1 atm from 20 degrees centigrade to 90 degrees centigrade. Work done by the gas is close to, take R as 8.31. So it is basically at constant pressure, so it is our isobaric. So we can say that our process is isobaric, and we know that for isobaric the work done W is equal to PV delta V, and in terms of the ideal gas equation we can write this will be equal to NR times delta T, and here T is our absolute temperature, so we can say our delta T, or we can just write it, to put the values directly, we can just solve it later on. So work done, number of moles is our half, so it comes as 1 by 2, R is our 8.31, and delta T will be equal to, we have 90 will be equal to 273 plus 90, that is our 363 minus 293, so we get this as our half multiplied by 8.31 times 70, and this 70 goes by 35, so we get the work done is approximately equal to 290.85 joules, or we can say approximately 291 joules. So option A is correct. Option A is our correct. Next question. Sorry. So we are given two Carnot engines A and B are operated in series. The first one, A, receives heat at T1 600 Kelvin, rejects to a reservoir at temperature T2. The second engine, B, receives heat rejected by the first engine and in turn rejects it to a heat reservoir T3, which is our 400 Kelvin. Calculate the temperature T2 if the work outputs of the two engine is equal. So we are given two engines A and B, and they are operated at the same, they are in series connected. Okay. So we can say, suppose this is our engine A and this is our engine B, and the first one receives the heat from T1 and gives out T2, and the second one takes this T2 and gives out T3, and in both cases it says that the work done is equal to same. So if for our A the work done is our WA and for B the work done is our WB, so we are given that work done because of A will be equal to work done because of B. Let us suppose that is equal to W, and therefore we can write that for our engine A, so we can say for A our WA will be equal to Q1 minus Q2, and which will be also equal to W, and we have for B we can say that our WB is equal to Q2 minus Q3, and this will be also equal to W. Okay. So from here, as both are equal, therefore we can write that our Q1 minus Q2 is equal to Q2 minus Q3. So from here we get that our Q1 plus Q3 is equal to 2 times Q2. Okay. And we can also write it in the form the ratio. So we can say Q1 upon Q2 plus Q3 upon Q2 is equal to 2. And with respect to temperature, the heat is nothing but they are temperature dependent. So Q1 will be our T1, Q2 will be our T2 plus Q3 will be our T3, and this will be also Q2 is equal to 2. And from here we can write that our T2 will be equal to T1 plus T3 divided by 2, and T1 is given to us as 6 plus 4, so this will be becoming as 600 Kelvin plus 400 Kelvin divided by 2, giving us that our T2 is equal to 500 Kelvin. So option B is correct. Next question. It says that a gas can be taken from A to B via two different processes, ACB and ADB. When path ACB used, 60 joule of heat flows into the system and 30 joule of work is done by the system. For path ADB, the used work done by the system is 10 joule and the heat flow into the system, the path ADB. So we have to find out the heat for our path ADB. PV diagram is given to us, so we are having two paths. One is through ADB and other one is from ACB. For ACB, the work heat flow as well as work done is given, and for ADB, work done is given. We have to find out the heat. And here the initial and final point are same for both the path. It starts from A and ends at B. So therefore, the delta U will be same. That the change in internal energy will be same for both paths. So we can say that initial and final states are same for our ADB and ACB. Therefore, we can write that our change in internal energy for path our ADB will be equal to change in internal energy for path ACB. And for our, we can use our first law, and first law gives us that our delta Q is equal to delta U plus delta W. So we can use for this ACB path. So we can say for ACB, we can write this as delta Q ACB is equal to delta U ACB plus delta W ACB. And for ACB, we are given delta Q as our 60. So this comes as 60 is equal to delta U ACB, and work done is given as our 30. So we get this delta U ACB is equal to 30 joules, and this will be also our delta U ADB. Now we can use again the first law for our ADB. So you can say for ADB, we can say that our delta Q ADB will be equal to delta U ADB plus delta W ADB. And we simply substitute the value now. We get our delta Q ADB will be equal to A, and delta U ADB is our 30 and plus 10, which gives us 40 joules. So we have option B is correct. Next question. It states that a thermometer graduated according to the linear scale reads a value x naught when in contact with the boiling water and x naught by 3 when in contact with the ice. What is the temperature of the object in degree centigrade if this thermometer in contact with the object reads x naught by 2? So we have given that the thermometer is having basically a linear scale. Therefore, we can write that we are having a linear scale, and we are given that the boiling water is x naught and with ice is x naught by 3. Therefore, we can say that for our ice point, which is our 0 degree centigrade, the reading is given as x naught by 3, and we have a boiling water, so we can say our boiling point, which is our 100 degree centigrade, reading is given as x naught. And because this is a linear scale, therefore we can write that for linear scale, the relationship can be written as T is equal to mx plus c. And now we can just, with respect to these two values, we can form the two equations. So we can say at x is equal to x naught by 3. Okay. And temperature will be equal to 0. Therefore, we get our 0 is equal to m x naught by 3 plus c. And at x is equal to x naught, boiling water temperature is of 100. So we get this as 100 is equal to m times x naught plus c. So we have two equations and two unknown. So we can just easily solve it. And we can say from our first equation, we can find out our c will be equal to, this will be minus m by 3 times x naught. And we substitute it in the second equation. We get 100 is equal to m x naught minus m by 3 times x naught. And this will be equal to 2 by 3 m x naught. So from here we get that our m will be equal to, this comes as 300 divided by 2, which will be equal to 150 times x naught. And we substitute it in the c, so we get our value of c is equal to, we have this as minus x naught by 3 times m, that is our 150 divided by x naught. And here this x naught 150 goes by 50, so we get c is equal to minus of 50. Therefore we get the equation that our T is equal to, m is our 150 x naught times x minus 50. Okay. And now we are given temperature at x naught by 2. Therefore we can say that at x is equal to x naught by 2, we can write the equation that T is equal to 150 x naught by 2 minus 50. X naught, then 50 goes by, 150 goes by 75. So we get this as T is equal to 75 minus 50, giving us T is equal to 25 degree centigrade. So we have option D is correct. Next question. It states that a heat source T is equal to 103 Kelvin. 1 second, this should be raised to power. Is connected to another heat reservoir at T is equal to 10 to the power 2 Kelvin by a copper slab which is 1 meter thick. Given the thermal conductivity of the copper is 0.1, the energy flux through it in steady state is. So we are given that we have heat source and reservoir connected by a slab. Okay, it is directly based on the formula which is called as a Fourier's law. So we can say that our Fourier's law, which states that our energy flux given as J is equal to K delta T upon delta x. And here delta x is our thickness and delta T is the difference in temperature. K is our constant, which is thermal conductivity, which is our 0.1. We can simply substitute the value. We get the flux is equal to K is our 0.1, delta T is different temperature 10 is to the power 3 minus 10 is to the power 2, and thickness is our 1 meter. That is our 1, which will be equal to our, this will be our 1000 minus 100, 900 multiply, this will become as 90 watt per meter square. So we have option A is correct. Next question. It states that if 10 is to the power 22 gas molecules, each of mass 10 is to the power minus 26 kg, collide with the surface perpendicular to it elastically per second over an area of 1 meter square with a speed of 10 is to the power 4 meter per second, the pressure exerted by the gas molecule will be of the order of. So in this case we are given that we have an area, suppose this is the area, and let us consider one gas molecule which is striking it perpendicularly, and its velocity is suppose given as v, and it's like strike elastically, so it is going to rebound back in this direction. Okay, and now its velocity will be minus of v. And we have to find out the pressure. So pressure is equal to force upon area, and force is equal to rate of change of momentum. Okay. And we can say that our pressure P is equal to force oblique area, and our force, that is our F, is our rate of change of momentum. A rate of change of momentum. So we can find out the rate of change of momentum, which is nothing but our delta P. Okay. Here let me write this as small p. Rate of change of momentum is small p. So we can say our this delta P will be equal to our mv and m minus of v. This comes as our 2mv, and mass and velocity are given to us, so we substitute them. We get this as equal to 2 into 10 is to the power minus 26 and 22, 26 and 10 is to the power 22, and this comes as our once again 10 to the power 4 velocity. So this comes as 2 into 10 is to the power minus 22, and we are given the elasticity per second. Okay, so we can say collision rate is given to us. Therefore we can say that collision rate is our 10 is to the power 22 collision in 1 second per second. Therefore we can say that our force which is F is equal to rate of change of momentum, and that comes to us as collision rate and change in momentum, that is 10 raised to power minus 22, which gives us 2 Newton, and therefore pressure P, force oblique area, which gives us 2 Newton per meter square. Okay, it is asking order, so this order will be 10 raised to power 0, and none of the option matches. Okay, so the correct will be 10 raised to power 0. Next question. It states that a massless spring constant 800 attached to the mass 500 gram is completely immersed in 1 kg of water. The spring is stretched by 2 cm and released so that it starts vibrating. What would be the order of the magnitude of change in temperature of the water when the vibration stops completely? Assume that the water container and spring receive negligible heat and specific heat of mass is 400 and that of water is 4184. Okay. So it is said that there is no heat received by the water container as well as spring. So it means the heat generated by the vibration of the mass is completely transferred to the water. Okay. So we can use just the conservation law. So first of all, we are going to find out the energy that will be associated with the spring. Okay. And then we can find out the temperature change. Okay. So we can say energy of the spring and in this case we have to remember that this energy of spring will be also your energy of the mass, because the mass is vibrating at the same you can say with each of our spring also. So energy of the spring, which will be our potential energy, is our E is equal to half k x square, and we substitute the value, we get this energy E is equal to half k is given to us as 800 and the x from the mean position is our 0.02, which gives us 0.16 joules, and we are given that all energy is transferred to our water. So we can say that all energy is transferred to water. Okay. So it means the energy associated with the water will be equal to our 0.16. Therefore, we can say that our heat energy given to water, suppose that is our Q will be equal to our E, and that is equal to 0.16. Now it is quite easy to solve. We know that the formula for Q is equal to over C multiplied by delta T. Okay. And from here we can say that our delta T is equal to Q upon C, and C is our total heat capacity. Okay, so we can say C is our total heat capacity. So we can say that this total heat capacity C will be equal to heat capacity of the mass plus heat capacity of our water. So we can write that our C will be equal to, and we have a mass is given as our M, and specific heat is given to us as 400. Okay, so we can say this heat capacity C will be equal to M mass of our mass, specific heat of our mass, plus mass of our water and specific heat of our water. So we simply substitute the values. Mass of the mass is our 0.5, specific heat of mass is given as 400, plus mass of water is given as 1 kg, and its specific heat is 4184. So we get the total heat capacity C will be equal to, this will be over 200 plus, so it comes as 4684, sorry, 200, 4384. Therefore our temperature delta T will be equal to, Q is our 0.16 and C we got as 4384. So approximately it is equal to 3.65 into 10 raised to the power minus 5. So we have asked the order, so it will be 10 raised to the power minus 5. So option D is correct. D is correct. Next question. It states that an ideal gas is enclosed in a cylinder at pressure 2 atm and temperature 300 Kelvin. The mean time between two successive collisions is 6 into 10 to the power minus 8. If the pressure is doubled, temperature is increased to 500 Kelvin. The mean time between two successive collisions will be close to. Okay. So here we have to, you can say, use the relationship that is directly based on the mean free time and then also along with their average velocity. Okay. So you can say that mean free time is our tau is equal to 1 upon n and sigma times V. Okay. And here n is our number density and is our collision cross section, and V is the average speed. And we know that the average speed V is proportional to square root of temperature. Therefore we can write this as V2 upon V1 is equal to square root of T2 upon T1. Temperature is given to us 500 upon 300. This comes as square root of 5 upon 3. and our number density, that is our N, will be equal to our P K upon T. Okay. So we can say that our N is proportional to P upon T. Therefore, N2 upon N1 will be equal to, this comes as our P2 upon T2 and P1 upon T1, giving us P2 T1 and P1 T2. And we substitute the value, we get this as our N2 upon N1. Pressure is our 2 and pressure is doubled, so this comes as our 2. P2 is our, P1 is 2, P2 is our 4, and temperature is our 300 and this is our 500. Okay, so here 0 and 0, so this 4 goes by 2, so from here we get this as 6 upon 5. Now we can easily find out our this mean free time. So we can write this as our mean free time ratio will be equal to tau 2 upon tau 1 is equal to, and we have this as 1 upon N2 V2 and 1 upon N1 V1. This comes as our N1 V1 upon N2 V2. And we can write this as our tau 2 upon tau 1 is equal to N1 upon N2 multiplied by V1 upon V2. N1 upon N2 is 5.6 and V1 upon V2 is our 3 by 5. So this ratio will be approximately equal to 0.645, and tau 1 is given as 6 into 10 to the power minus 8. Therefore, we can say that our tau 2 is equal to 0.645 times tau 1, 0.645 into 6 into 10 to the power minus 8. So we get this about tau 2 will be equal to approximately 4 into 10 to the power minus 8 seconds. So option number A is correct. Next question. It states that a vertical closed cylinder is separated into two parts by a frictionless piston of mass m and of negligible thickness. The piston is free to move along the length of the cylinder. The length of the cylinder above the piston is L1 and below the piston is L2, such that L1 is greater than L2. Each part of the cylinder contains n moles of ideal gas at equal temperature T. If piston is stationary, its mass is m, will be given by R is the universal gas constant and G is the acceleration due to gravity. So we can just draw the approximate figure for that. So this is a cylinder and in between there is a piston. Suppose this is the piston, okay, and above it is given a length as L1, and below we are going to have length L2, and this is said to be in equilibrium, okay. And above we have number of moles as N, temperature T, below also number of moles as N, temperature is T, okay. And in the downward direction we are going to have a force of mg because of the weight of the piston, okay. And so if the piston is in equilibrium, so we can say the pressure above should be equal to pressure below, okay. So we can say that our piston is stationary, piston is stationary, therefore we can say that pressure above is equal to pressure below, okay. And therefore we can write that in the downward direction we are going to have a force of mg, so the pressure because of this mg will be equal to mg upon A. So we can say the pressure because of this mg will be equal to force mg upon A, where A is the cross-sectional area of this disc, okay. And therefore we can write that our P1 should be equal to our P2 plus mg upon A, okay. And we can use our ideal gas law, and we can assume that upper we have volume V1, in the downward we are having volume V2. Therefore we can say that our volume V1 will be equal to area into L1, and we have volume V2 which will be equal to area into L2, because the area of the cylinder will be same, okay. And now we can just use our ideal gas law. So we can say from ideal gas law we can write that PV is equal to nRT. So therefore we have two separate containers, therefore we can write this as P1 V1 is equal to nRT, and we can write P2 V2 is also equal to nRT. And from the first part we can write that our P1 is equal to nRT upon V1, which is equal to nRT upon area multiplied by L1. And from the second part we can write our P2 is equal to nRT upon V2, which comes as our nRT upon A multiplied by L2. Now we can write the force balance equation. So we can say our force balance and we know that the force is equal to pressure multiplied by area, so we get this as our P1A is equal to P2A plus mg. Same equation but written in the force form now. Okay. And we can substitute our P1 and P2. P1 was our nRT upon AL1 is equal to, and multiply by A, and P2 is our nRT AL2 multiplied by A plus mg. Here A cancel out, so we get from here that our mg is equal to, we can take nRT as common, and this get as our 1 upon L1 minus 1 upon L2. Okay. One second. Let me write it first. So we can write that our mg, or we can say our m, is equal to nRT upon g, and this comes as our L2 minus L1 upon L1 L2. Okay. And we have to remember that we are given that our L1 is greater than L2. Okay. One second. Let me. So L1 is greater than L2. Therefore, yes. So here we are going to have our pressure P1. Sorry. This will be a pressure P1 and this will be a pressure P2. And this we cannot write, okay, because pressure cannot be equal. That was, okay, we have to remember, because P1 is our so our L1 is greater, 1 second, let me write it here. L1 is greater than L2, that is given to us, and we know that our V1 is equal to area times L1 and our V2 is equal to area times L2. Therefore, we can also say that our V1 is greater than our V2. Okay, and our pressure P1 is equal to, or rather we can say pressure is inversely proportional to our V1. Thus we can write that our P1 upon P2 is equal to V2 upon V1. Okay, therefore we can further write it as we are having V2 upon V1 is less than 1. Therefore, we can say P1 upon P2 is less than 1, giving us that P1 is less than P2. Therefore, P2 is greater than P1. Let me write it here. P2 is greater than P1. And so we need to change the and therefore we can also say that our F2 upon area is greater than F1 upon area, giving us F2 is greater than our F1. Okay, so only thing is the sign is needs to be adjusted. Answer will be same. Yeah, got it. Okay. Therefore, our F2 is greater than our F1. Thus, we can write that our P2A will be equal to our P1 plus mg, P1A upon mg. Yeah, so this is our equation. I have written it as, yeah, so there is change for this equation. Okay, that's the force balance. So we get P2A is equal to this one. The rest of the things will be same. So only is going to change. This will be our same answer, but so you can say our mass M is equal to nRT upon G, and we are having L1 minus L2 upon L1 L2. So we get this as our L1 minus L2 upon L1 L2. Option A is correct. Option A is correct. Next question. It states that 3 Carnot engines operate in series between a heat source at a temperature T1 and a heat sink at a temperature T4 as in figure. There are 2 other reservoirs at the temperature T2 and T3 as shown with T1 greater than T2 greater than T3 greater than 4. The 3 engines are equally efficient if basic is given. So initially we have 3 engines E1, E2, E3 connected with the sink and reservoir, that is our source and sink T1, T2, T3 and T4. Okay. And all these in series. So let us assume that the efficiency of first engine is our nu1, nu2 and nu3. And the general formula for efficiency of a Carnot engine, you can see our efficiency for Carnot engine which is given as nu, and that is our nu is equal to 1 minus temperature of our sink, temperature of our source. Okay, so we have 3 engines. We can write this equation in according to 3 times. Okay, so we can say for engine 1, nu1 will be equal to 1 minus T2 upon T1. For engine 2, we can write say nu 2 is equal to 1 minus T3 upon T2, and we have engine 3 is equal to nu 3 is equal to 1 minus and T4 upon T3, and we are given that all these efficiency are equal. Nu 1 is equal to nu 2 is equal to nu 3. This is given to us. Okay. So therefore we can equate our first two engines, and we can say that our nu 1 is equal to nu 2. This gives us 1 minus T2 upon T1 is equal to 1 minus T3 upon T2. Here 1 and 1 minus and minus goes away, so we get this as our T2 upon T1 is equal to T3 upon T2, and therefore we get that our T2 square is equal to T1 times T3. Okay. And similarly we equate our N2 and N3. So we get our nu 2 is equal to nu 3. Therefore we can write that our 1 minus T3 upon T2 is equal to 1 minus T4 upon T3. And here also this 1 minus goes away. This gives us our T3 upon T2 is equal to T4 upon T3. And from here we get that our T3 square is equal to T2 times T4. Finally we equate nu 1 and nu 3. Nu 1 is equal to nu 3, which gives us 1 minus T2 upon T1 is equal to 1 minus T4 upon T3. So this gives us T2 upon T1 is equal to T4 upon T3. Okay. And now let us substitute the values which we found out. So let me rewrite here. So we get our T2 upon T1 is equal to T4 upon T3. Okay. So from here we get our T2 is equal to T1 T4 upon T3. Okay. And let me write this equation number 1, 2 and 3. Okay. So this is T2 and okay, so first of all let's find out the ratio of 1 and 2. So we can say from equation 1 and 2, 1 and 2, we get T2 upon T3 whole square is equal to T2 is our T1 T3 and T3 is our T2 T4. Okay. And so we cross multiply this T2 and T3, we get this as our T2 upon T3 whole cube will be equal to T1 upon T4. Okay. And therefore we can say that our T2 upon T3 will be equal to T1 upon T4 whole raised to power 1 by 3. And we get that our T2 is equal to T1 upon T4 whole raised to power 1 by 3 times T3. Okay. And now we are going to use our equation number 3. Equation number 3 is also our T3 is T2, so we can say that this will be equal to our T1 T4 divided by T3. And now we simply cross multiply them. So we get this as T3 square will be equal to, this is our T1 and it will be, let me segregate it. So this is your T1 divided by T1 whole raised to power 1 by 3 multiply by T4, and this is multiplied by T4 whole raised to power 1 by 3. And this gives us that our T1 1 minus 1 by 3, and that will be giving us 2 by 3, and we have the T4 1 plus 1 by 3, which will be giving us 4 by 3. Therefore, if we take square root both side, we get our T3 is equal to T1 2 by 3, T4 4 by 3, and whole raised to power 1 by 2, which can be written as T1 1 by 3 and T4 2 by 3. And we can further write it as T1 T4 square whole raised to power 1 by 3. I think this is the correct format of the answer. Yeah. So we have this as our, okay, let me simplify it. So we get our T3 is equal to T1 T4 and whole raised to power 1 by 3. So this is our T3, and we already know our relationship between T2 and T3, that is equation number 3. Okay. Or we can use this equation. I think this will be much more better. Okay, so we are going to use this equation. So we can say our T2 is equal to, this is our T1 upon T4 whole raised to power 1 by 3 multiplied by T3. So we get this as our T1 1 by 3, T4 1 by 3 multiplied by T1 1 by 3 and T4 2 by 3. So we get this as our T2 is equal to T1, this will be 1 by 3 plus 1 by 3, which will be giving us 2 by 3. And we have T4, this will be 2 by 3 minus 1 by 3, giving us 1 by 3. Therefore, we can write about T2 is equal to T1 square T4 whole raised to power 1 by 3. So we have our T23. Okay. So we have a T2 and T3, and our T2 is T1 square. So T2 is T1 square. T1 square is only this one, so this is the correct one. Option B is correct. T3 is our T1 and 4 square. So option B is correct. Next question. It states that a 25 into 10 to the power minus 3 meter cube volume of cylinder is filled with 1 mole of O2 oxygen gas at room temperature 300 Kelvin. The molecular diameter of O2 and its root mean square speed are found to be 0.3 nanometer and 200 meter per second respectively. What is the average collision rate per second for O2 molecule? Okay. And we know that our collision rate, that is our standard formula. We can say that our collision rate, that is our Z is equal to our N and times V. Here N is our number density and our sigma is our pi d square, which is also called as a collision cross section. Collision cross section, and V is our approximately equal to VRMS. Okay. So let's find out all these parameters. So we start with number density, that is our N is equal to capital N, that is our mole, number of oxygen, total number of, so we get this as N is equal to 1 into, and we have this as 6.022 into 10 to the power 23, and volume is our 25 into 10 to the power minus 3. Therefore we get N is equal to approximately 2.409 into 10 to the power 25. Now we can find out our D is our cross section is equal to our, I think it is given to us 0.3 nanometer. So this comes as 3 into 10 to the power 10 meter, and from here we can find out our sigma is equal to pi multiplied by 3 into 10 to the power 10 whole square. So approximately this will be equal to 2.827 into 10 to the power minus 19 meter square. Therefore we can say our collision rate, that is Z is equal to 2.409 into 10 to the power 25 multiplied by 2.827 into 10 to the power minus 19 multiplied by 200. So we get that our Z is approximately equal to 1.362 into 10 to the power 9. Okay. Or we can say this will be 0.2 into 10 to the power 10. So approximately 10 to the power 10, option A is correct. Next question. It states that the number density of the molecules of gas depends upon their distance r from the origin, as n of r is equal to n naught e raised to power minus ar. This should be raised to power 4. Then the total number of molecules is proportional to, and so we can say that the total number of molecules let us suppose that is n will be equal to integral of our number density, which is dependent on the distance, and the small volume we have taken as dV. And this dV will be equal to, our volume is 4 by 3 pi r cube. You can say volume is equal to 4 by 3 pi r cube. Therefore we get our dV is equal to 4 pi r square times dr, and we substitute it. We get our n is equal to integral, and this is given n naught e raised to power minus ar r raised to power 4, and this we have as 4 pi r square, and we have dr, integral from 0 to infinity. Okay, so we can just take out the constant things, which is our 4 pi n naught integration 0 to infinity, and we have this as r square e raised to power minus a r raised to power 4 d of r. So we make a substitution. We say that let u is equal to r raised to power 4. From here we can say r is equal to u 1/4, and d of r is equal to 1 by 4 u minus 3 by 4 du, and our r square will be equal to u 1 by 2. Therefore we can write that our n is equal to 4 pi n naught, and this is 0 to infinity. Limits are not going to change, because when r is 0, u is 0, and when r is infinity, u is also infinity. And we get this as our 1 by 4, r square is 1 by 2, and our e raised to power minus au, and this comes 1 by 4 u raised to power minus 3 by 4 d of u. Okay, so we can combine these two u's. This will be 1 by 2 minus 3 by 4, which will be giving us 2 minus 3, that is minus 1 by 4. So we get that our 4 pi n naught integral 0 to infinity, 4 we can take common, and this comes as u raised to power minus 1 by 4 e raised to power minus au d of u, and this 4 and 4 goes away, and this particular function is in the format of our gamma function. Okay, so we can say we are having a gamma function which gives integral 0 to infinity u of n minus 1 e raised to power minus a u and d of u, and this gives us a function of about n divided by a raised to power n, and here n is equal to 3 by 4. Therefore, we get our n is equal to pi n naught, and a function of n is about 3 by 4 and divided by a 3 by 4, and we are asked about only proportionality. Pi is constant and this function value will be also constant. So pi is constant and this is also constant. Therefore, we can say that our n is proportional to our n naught a raised to power minus 3 by 4. So option A is correct. This is not A, this is alpha. Sorry, my mistake, but anyways it doesn't matter. Okay, we have to take this as A, not A but as alpha. So I can write this as n is proportional to n naught alpha 3 by 4. So you can say option A is correct. A is correct. So this completes all the 21 questions. All these questions from the mains part only, 2019 mains. So this completes all the 21 questions. Thank you.